Today in this video, we'll be talking about hypergeometric distribution. In our previous videos, we talked about binomial distribution. So let's first get into a brief discussion about binomial distribution, and then we will move on to the hypergeometric distribution just to understand what exactly is hypergeometric distribution. So first of all, in a binomial distribution, we saw that all the trials are independent, right? So that the probability of success remains unchanged from trial to trial. Like as in, let's talk about a dice. In a dice, we know that when we are throwing a die, we can get any of the 6 outcomes. It can be 1, 2, 3, 4, 5, 6. Any of the number can appear on the die, right? So now let's suppose I am finding out the probability of getting an even number, right? So when I'm finding out the probability of an even number, I'll simply say it will be 1, 2, 3, 3 upon total number of cases are 6, so it will be 3 by 6, that is half, right? So when I'm throwing up my first die, I'm saying what is the probability of getting an even number? So it will be half. Now again I'm saying, okay, now this was my first trial. Now I'm again doing my second trial. Now in my second trial, again I'm throwing the die. So what is the probability of getting an even number? It will again be half. Now in my third trial, what is the probability of getting an even number? It will again be half. So we are saying that the probability of success remains unchanged from trial to trial, right? So thus in a binomial distribution, all the trials are independent of each other, right? So now we can also understand this independence of trials in a form. Let's suppose I have a bucket. In that bucket, I have few balls, right? Let's suppose I have 10 balls. Out of those 10 balls, 6 balls are blue in color, right? And 4 balls are, let's suppose, red in color, right? Now I'm picking up a ball. So what is the probability of getting a blue ball? So it's simple. Probability of getting a blue ball is 6 upon 10, right? Or we can simply say 3 by 5. Now this was my first trial. So I was saying what was the probability of getting a blue ball. Now what I'm doing is I took out a ball and let's suppose that turned out to be blue or maybe red. It can be any color. So now what I'm doing is I'm now replacing this ball back into the ball in that bucket. So I'm putting that ball that I picked up in my first trial back into the bucket. So basically I'm saying I'm replacing it, right? So in that case, when I'm saying in my second trial, what will be the probability of getting a blue ball again? It will remain unchanged. It will be 6 by 10 again or 3 by 5. So it is unchanged. Why? Because whatever ball I picked up in my first trial, I am putting it back into the bucket. So now that bucket contains again the same number of blue balls and same number of red balls as in the previous case. So it has all complete 10 balls in my second trial as well. But now in my third trial, let's suppose what I'm doing is I'm picking up a ball in my second trial. So, or rather let's separate it. Now again I'm taking another experiment. Let's say this is experiment number 2. In my experiment 2, this was my experiment 1, I am picking up a ball, right? So in my experiment 2, trial number 1, I am saying what is the probability of getting a blue ball? You will say that this is simply equal to 6 upon 10, that is 3 by 5, right? So now I have picked up a ball and let's suppose that ball that I picked up was a red ball. So when I picked up that red ball, I've kept it aside, right? So now what can I say? My bucket now has 9 balls, right? How my bucket has 9 balls now? Simple. So let's suppose now this is my bucket. In that bucket, I have 9 balls, and in those 9 balls, my 6 balls are blue and only 3 are red. Because one ball that I picked up in my first trial, I've kept it aside. Now when I am saying what is the probability of getting a blue ball in my second trial when I've already kept that selected ball aside, not back into the bucket. So what will be the probability now? Now the probability of getting a blue ball will be 6 upon 9. 6 balls out of 9 balls. So the probability becomes 2 by 3. Now what has happened? Now what has happened is that from trial to trial, the probability of getting a blue ball is getting changed. Right? The probability is changing. So since this is changing, now we cannot use the similar concept of binomial distribution. Why? Because each trial is not independent of the previous trial. Over here in our experiment 1, since I was replacing my picked up ball, that the trials were independent. But over here now, since I'm not replacing my picked up ball, I'm keeping that aside, and my bucket is basically number of balls in the bucket are reducing with each trial. So obviously the probability is getting changed. Probability of blue ball is getting changed in each trial. So now these trials are not independent. So in these kinds of cases, binomial distribution cannot help us to find the probabilities. So what do we pick up is, we pick up we use hypergeometric distribution in order to find the probabilities for such cases, right? So now if I want to find out or I need to simply find out a formula for a hypergeometric distribution that can be generalized. So let's talk about that. So to illustrate, suppose our population size be n, right? And this n contains two types of elements. One is n1 is our number of first type of elements, and n2 is the number of second kind of elements, right? So let me denote element of one kind and element of second kind, or we can also simply talk about this as basically another kind. We can also talk this about in terms of the balls. One is blue ball and one is red ball. So here we are talking about n1 as one kind of element and n2 as another kind, other element of another kind, right? So now out of this I am picking, or we can also, let's talk about this as success and this as failure. Let's say our n1, let's say we are finding the probability of n1 kind of elements, and so this is our failure because we are not finding its probability, right? So n2 is the failure and n1 is the success because I'm trying to find out the probability of getting n1 number of elements, right? So now let's suppose I'm picking up a sample, and let's suppose the sample size is denoted by small n, right? So sample size is denoted by small n, right? And let's suppose I'm trying to find out the probability of x is equal to small x. That is, I'm trying to find out the probability that when I'm picking up the n balls from this capital N, from my entire population, when I'm picking up a sample size or a sample of these small n kind of elements, then what is the probability that what is the probability that element of one kind is x now, x, right? So basically I'm saying that I'm getting x elements out of these n1, right? So what is the probability that x elements be chosen out of n1? Now if x elements are chosen out of n1, right? So if out of n1, if I am choosing x elements, then it's quite obvious that out of n2, how many elements do I want? I want n minus x elements, right? Because I'm picking up n elements in total out of the population size. Then I'm saying I want x elements to be of kind n1, right? So now for n2, obviously out of the sample, if I'm deducting all the elements of n1 kind, so I'll get n minus x will be my elements of n2 kind. So now I need the probability that x is equal to x. What is this probability? So first of all, so in order to find the probability that x is equal to x, or that we are getting n x elements of one kind out of the sample size of this small n. So for that, first of all, we need to find what is the probability. We need to find, or let's say not the probability, we need to find the number of ways in which n elements can be selected from n elements, right? So we were about to find the number of ways in which n elements can be selected from n elements, capital N elements, right? So this is simply the concept of combinations, right? So we need to find n elements out of n elements. This can be simply said as n, C, n, right? So by this we can find the number of ways in which n elements can be selected from n elements, right? So now after this, similarly, if I want to find, let's say, number of elements, right? Number of elements or number of ways in which x elements can be selected out of n1 elements. Why I am doing this? I am doing this because out of n1 elements, I need x elements, right? And similarly, we also need to find the number of ways in which n minus x elements can be selected out of n2 elements, right? These are the two things that I need to compute now. So now if I want to find the number of ways in which x elements can be selected out of n1 elements is simply n1 c x, right? Again the combination. And if I want to compute the number of ways in which n minus x elements can be selected out of n2 elements is simply n2 C n minus x, that is n2 elements out of n minus x elements out of n2. So accordingly, the total number of ways in which x elements of the first kind and n minus x elements of the second kind can be selected is simply given by the product of n1cx and n2c into n minus x, right? So this is that if I'm, let's suppose there are n population sizes n, out of which we have n1 of one kind, n2 of second kind, and out of which if I want to pick x elements of n1 kind and then remaining n minus x elements of n2 kind. So this is n1 into cx, that is my first, I'm picking up these and then I'm saying okay, now I need n minus x elements of n2 kind, right? So this is this. So this is the number of ways in which we can pick x elements of n1 kind and n minus x elements of n2 kinds. Let me write it now. X elements of n1 kind. I am putting this and. So this and means multiplication. N minus x elements of n2 kind, right? So now this is given by this. So thus we can say that our probability of x is equal to x is simply equal to number of ways in which we can pick x elements from n1 kind and n minus x elements of n2 kind divided by the total number of ways in which we can pick up the n elements out of capital N population size. So this is fine. So here we also know that n is equal to n1 plus n2 and so n1, that is the number of n1 kind of elements that were picked as x, and small n2, that is the number of kind of elements that of second kind that we have picked is n minus x. Fine. And n1 plus n2 is equal to n. So this is fine. So what we have done is that number of ways in which we can pick x elements out of n1 elements multiplied by number of ways in which we can pick n minus x elements out of n2 elements upon the total number of ways in which we can pick up the n elements, right? And this entire formula gives us the hypergeometric distribution, right? So it's quite easy. So now let's move towards mean and variance. So for this mean and variance, I won't be moving towards the derivation of this. I'll be simply talking about the formula. Now the thing is similar, that n is population size, right? Small n is sample size, and n1 is the subset of element of one kind. So basically it's the same as these. So please consider all the notations are same that I have used over here, right? So now our mean or the expected value or mean of a hypergeometric distribution is given by n, small n, into n1, that is the number of success elements, right? So n1 was our success elements there, so I am simply writing over here it as n1 upon total n, right? So can you see this is somewhere related to the binomial distribution over, basically this is the n1 upon n is simply the probability of success, and we are multiplying by n, so that was np, and this is n into n1 upon n. So it's related, right? Because it's more or less similar, except for the thing that in binomial distribution independence all the probabilities or everything was all the trials were independent, but in hypergeometric distributions trials are not independent. So now variance is simply given as n into n1 upon n into n2 upon n into capital N minus small n upon capital N minus 1. So this is the formula for variance and this is the formula for mean. I am not going to go towards its derivation because it's not required for business statistics, right? So now let's take an example. So there's a question. A set of 10 tubes is received which is known to contain 3 defectives. So out of 10 tubes, right, defective tubes are 3 and non-defective tubes are, so since 3 are defective, so the number of non-defective are 7. If a sample of 3 tubes is taken randomly, okay, so basically this 10 is our capital N population size, or let's write it down. So now, so we simply know that this 10, what is this 10? This 10 is simply our capital N. This, now we are saying we need to find if a sample of 3 tubes is taken randomly. So small n is equal to 3, capital N is equal to 10. What is the probability that it will consist of 2 good tubes and 1 defective, and also find expectation and variance for good tubes. So we are saying good tubes means non-defective. So that is, this represents our N1, that is N1 is equal to 7, and defective tubes are N2. So right, N2 is equal to 3, right? So first of all, we need to find if a sample of 3 tubes is taken randomly, what is the probability that it will consist of 2 good tubes and 1 defective, and find expectation of variance of good tubes. This is the thing now. So I have taken N1 as 7, like N1 is non-defective, because we need to find the expectation and variance for good tubes, right? Had it been defective tubes, we would have taken N1 is equal to 3, right? And in finding the probability, it does not matter what we are taking as N1 and what we are taking as N2, right? So probability that X is equal to, that is number of good tubes is equal to 2, right? So when we need to find that, that's simply equal to, first of all, out of 7 bad tubes. Okay, let's write down the formula first. So over here, probability of x is equal to x is simply equal to n1cx into n2cn minus x upon ncn. Right? So probability of x is equal to 2 is n1cx. n1 is 7. 7c2 into n2 is 3. 3c, n minus x is simply 3 minus 2 upon capital N is 10, c 3. So this is simply 7c2 into 3c1 upon 10c3. Right? So let's solve this out. This is simply 7 into 6 upon 2 into 3. This whole upon is 10, or let me just write down so that it's a bit clear for you. Let me write down over here. So this is 7 into 6 upon 2 into 1 into 3 upon 10 into 9 into 8. So it's my way of calculating these combinations. You can do it either way. 2 into 1. So let's solve this out. This is simply this into 3, and this cancel out with this 3, this with this 5, this 3 cancel out with this. So this becomes simply 21 by 40, right? So this is simply equal to 0.525 because 21 by 4 is 5.25, so this has become 0.525, right? So this is simple way of calculating the probabilities. After that, we are asked to find expectation and variance for good tubes, right? So expected value of good tubes is simply equal to, let's suppose expectation or expected value is simply equal to, this is n into n1 upon capital N, right? So small n is 3, then it's 7. So 3 into 7 by capital N is 10. So this becomes 21 upon 10, which is equal to 2.1. Now we need to find the variance. So variance was simply equal to small n, n1 upon n into n2 upon n into capital N minus n upon capital N minus 1. So now putting in the values, the small n is 3, n1 upon n is 7 upon 10, n2 upon n is 3 upon 10, capital N minus small n means 10 minus 3 upon 10 minus 1. So this is simply equal to 3 into 7 by 10 into 3 by 10 into 7 upon 9, right? So now let's solve this out. So this becomes 49 upon 100, which is equal to 0.49, right? So our variance for good tubes is simply equal to 0.49, and our expectation for good tubes is 2.1. And this was the probability of getting 2 good tubes, right? So this is what is all about hypergeometric distributions. I hope you like this video. Do subscribe this channel for more videos. Thank you.